Okay, so in this we will see uh, the Newton-Raphson method for system of equations. So let me write it down. System of equations. So in the Newton-Raphson method, what we were doing, if you remember that, suppose this is my function f, then at given this x k, we were trying to find out a tangent for that particular iteration, and wherever that tangent was going through this x-axis, that point was considered as xk plus 1. Uh, in this case, since there is not a single value of x, it is a vector. So x is nothing but x1, x2, x3 up to xn. So this is the idea, and then we have function f1, f2 going up to fn. So what essentially we are doing, so suppose for this x, this f1, so this is my function f1, we will draw the tangent for x1k, and then we will find out x1k plus 1. For function from function f2, suppose this is function f2, we will use x2k, and then we will find out this value x2k plus 1. So this is the idea. At each function we will try to find a tangent, and then wherever this tangent cuts the x-axis, where the x-axis is related to a particular component of x vector, it is not x is not a single component here. So this tangent mean, if you remember, then that we discussed, this tangent means nothing but first order Taylor series approximation. I hope you remember this. So this was nothing but the first order Taylor series approximation, and we saw initially that we could write Taylor series in 3D, 2D. We have seen that. Here we will write Taylor series is n dimensions. So it is basically, since there are n variables, so we will write the Taylor series is in n dimension, but up to first order approximation only. So what I am saying essentially here is that for function f1, we are saying that x1 plus delta x1, x2 plus delta x2 going up to xn plus delta xn is nothing but f of x1, x2, sorry, this is f1 up to xn plus delta x1 df over dx1 at x1, x2 up to xn plus delta x2 df1 over dx2 x1, x2 up to xn plus, then we will have delta xn df1 over dxn, where x1, x2 going up to xn. So for every function we will write down this, and at every iteration we will consider that f1 x plus delta x is 0, where this x plus delta x is x1 plus delta x1 comma x2 plus delta x2. This is 0 at every iteration. We are considering this to be 0. So this will give me a functional form in such a way that we will have this vector 0, and that is nothing but f1 value, f2 value up to fn value, and at xk, where this x is vector, this is not a single value, this contains x1, x2 and up to xn, plus then we will have this matrix del f1 over del x1, del f2 over del x2 going up to del f1, sorry, this is del f1 over del xn. Then we will have the del f2 over del x1, del f2 over del x2 going up to del f2 over del xn. and then we will have del fn over del x1, del fn over del x2 going up to del fn over del xn, and then we have this delta x vector. So we have this, and this, remember, this will be at the old value of x, and then we have delta x1, delta x2 going up to delta xn. Okay, so this will give me that x vector at k plus 1 is nothing but x vector at k minus Jacobian inverse. So this is my Jacobian matrix. This I call it as Jacobian matrix. This is defined as Jacobian matrix. Jacobian matrix inverse, and then we will have the function value at xk. This is also at xk. So what we got out of this, that vector k plus 1 is nothing but vector k xk minus Jacobian inverse at xk function at xk, where Jacobian inverse is defined as adjoint of Jacobian matrix upon mod of Jacobian matrix. So this is the Jacobian inverse of the Jacobian matrix, where mod of j should not be equal to 0. So this is the condition. So this is how we can find out the solution of system of equations using this Newton-Raphson method. So with this video we are done with this root finding problems. There are other methods also, like Beer-Stroh method, which is used to find out the complex roots also, but I am not going to talk about those complex methods in this video series, because this is not an advanced computational methods video series. Maybe in the next semester I will record the advanced computational methods video series, where we will talk about advanced matrix solver algorithms like multigrade or steepest descent gradient based methods. We will talk about them in details if I get to record the advanced computational methods video. But in this video lecture series, or I would say in this part that was related to root finding, we talked about bracketing methods, in which we learned two methods, basically bisection methods and regular falsy method, if you remember. Then we came to the open methods, and in open methods we learned about this fixed point iteration method. Then we talked about Newton-Raphson method, and then we further talked about second method and Euler method, and I gave you example of each and every method, so you can understand it in a better way. So I hope this is useful to you. These videos I am recording to fulfill the requirement of this PMRF scheme, since we are supposed to teach in outside engineering colleges, but due to COVID I am not able to teach outside, so I am recording these video lectures. And if we are given the permission to record the video lectures in the next semester also, so I will record that advanced computational methods in engineering in the next semester. There we will talk about this Beer-Stroh method and recursive methods. Okay, thank you.